All right, let's begin. I don't think we'll get more people today. Okay, fine. So we will discuss few things about week 10 today, and on Saturday we will do problems. Today also we'll do problems. So majorly on given a frequency impulse response to an LTI system. Okay, so given an input also to you, can you get the output? Okay, so previously we have to do convolution, but can we use Fourier transforms and make our lives simpler? That is one thing. And we will also solve, so in week 10 also professor has solved most of the lectures. We have solved how to compute Fourier transforms of some signals, right? Whether they are finite signals or infinite signals. And U of t looks very easy signal, right? So we have been studying U of t, the step signal, unit step signal. But computing its Fourier transform is really challenging. So so once you understand how to compute Fourier transform of the signal u of t, then we can use that and compute a Fourier transform for a constant DC signal, and even sine signal, sine t, some, right? So when t greater than 0 it takes +1, and when t less than 0 it takes -1. So that signal, and the e power phasor e power j omega t, omega naught t, and of course sinusoidal signal. So even the periodic signals we can find the Fourier transforms. Even the signals like infinite energy, which is u of t, for that also we can find the Fourier transforms. Okay, so these are really important. You should get used to this. Given any kind of signal, you should be able to compute its Fourier transform. And given an LTI system to you, given its impulse response, you should be able to compute its frequency response, which is also called as transfer function. So I hope most of you have heard about it. Hj omega, capital Hj omega. Right. So all those things were covered in week 10, and I will discuss few concepts as well as problems. Okay. So that's what the feedback is about, I guess. So what we do is we'll start with computing the Fourier transform of u of t. This is really important, and it has been extensively discussed in the lecture also. But let us quickly understand it again. Okay, so let's say we have the signal u of t, and we are interested to find its Fourier transform. Oh, is my voice breaking? Can somebody confirm? Is my voice okay? Yeah, yeah. So maybe Pratibha, can you rejoin, or can you check your internet connectivity? So from my end also, I hope it's clear only. So I don't think any issues from my side. All right. So when we want to find its Fourier transform, usually if we try to use the formula that we know, right? So we try to compute xj omega. So what will be the formula? Or how should I compute the Fourier transform? I have to integrate from minus infinite to plus infinite x of t e power minus j omega t dt. Right, so if x of t is u of t, if I substitute u of t, then the limits will change. We know what u of t is. U of t is 1 when t greater than 0, and it will be 0 when t less than 0. So this will just simply become integral from 0 to infinite 1 into e power minus j omega t dt. And when we integrate, what will happen? E power minus j omega t by minus j omega, infinity and 0. When I substitute infinite, it will just simply become 0. When I substitute 0, it will become 1 by j omega. And this is, you see, omega comes in the denominator. So omega not equals to 0. But what if, or what happens to my transform when omega is equals to 0? Right? So that is also we should take care, no? So for that, what we do is, we can't do it using this particular u of t directly. We use limits. Okay, so what we say is, I'm not going to consider u of t will be like this, but I'm not going to consider u of t, whereas I'm going to consider a series of exponentials, right? So I'm going to consider e power minus at u of t instead of u of t. Okay, so what I say is, I'm going to look at e power minus at u of t as a tends to 0. Okay, so what will happen to this curve? So e power minus at u of t, we know, if we plot it, it would look something like this, right? For some positive a, right? And this will be 0, like this. As I decrease a, what do you think will happen? If I decrease the value of a little bit, this will become like this. As I further decrease and come closer and closer to 0, so you see this e power 0, this whole expression will come closer to u of t, right? So it will slowly, as a comes near to 0, this will more or less become u of t. Okay, so now instead of u of t, what we say is, we consider this particular limit and we equate to be u of t. We call this as u of t. As a tends to 0, e power minus at u of t will also be u of t. Okay, so now instead of computing Fourier transform for this, we will compute Fourier transform for this. Okay, so if I compute the Fourier transform for this limit a tends to 0 e power minus at u of t, I will pull out limit outside, right? So I can do that. If I do that, limit a tends to 0, Fourier transform of e power minus at u of t. And this we have already seen, right? So this, we all know it is 1 by a plus j omega, right? I hope we have did this in week 9, right? When a greater than 0. So note that a here is greater than 0. We know the Fourier transform of e power minus at u of t. Even if you don't know, you just use the formula. You will arrive to 1 by a plus j omega. Okay. So once we reach here, we boil down to this particular expression. So limit a tends to 0, 1 by a plus j omega. Again, if I just simply substitute a is equals to 0, again I will end up getting 1 by j omega, and there again I am restricted to omega not equals to 0. I should also talk about omega is equals to 0. Now what I will do is, I will multiply the denominator with its complex conjugate. Okay, so a minus j omega, which is its complex conjugate. Once if I am dividing, if I am doing that in the denominator, I should also do that in the numerator, because I should have the same value, right? So when I am doing something in the denominator, I should do the same thing in the numerator also, so that the expression value should not change. So if I do this, we will get a minus j omega divided by the denominator. If you multiply, you will see that you will get a square plus omega square. Okay. So now this I will write as limit a tends to 0, a by a square plus omega square minus limit a tends to 0, j omega by a square plus omega square. Now you see this expression, this is really easy to work out. So we have when omega is equals to 0, you can see that the numerator will be 0 and the denominator will be a square. So this whole expression will just be 0. So this will be 0 when omega is equals to 0. And when omega not equals to 0, so this limit as a tends to 0, this will vanish. We'll have j omega by omega square, which will give me j by omega. Right? So this is j by omega when omega not equals to 0. Or if I include this minus also, I will have minus j by omega when omega is not equals to 0. When I come to this particular expression, again here also when omega not equals to 0 is an easy case to see. When omega is not equals to 0, as a tends to 0, the numerator will be 0, but the denominator will not be 0 because omega is not 0. So overall expression will just simply become 0. Right? When omega not equals to 0, it is 0. When omega is equals to 0, you will see that if this is 0, you will have 1 by a square, which is 1 by a. As a tends to 0, 1 by a goes to infinite. It is something like at omega is equals to 0, this value is just suddenly blowing up. So we know one signal where it is 0 at every other place and suddenly it has infinite value at a particular point. Right? So which signal is that? We know the signal. Right? It is this signal. So it is everywhere 0 except at so this is just simply blowing up. It is going to infinite. Right? So this we have seen, which is delta. Right? So recall all these things. So this will simply become delta, but delta of omega will have area under the curve to be equals to 1. Right? So we should be sure that if I integrate this from minus infinite to plus infinite, if I am getting 1, then of course that will represent another way of representing delta of omega. Okay, so even in the lecture also it is discussed. If you didn't understand here, just go back to the lecture. The same thing I am discussing. Okay. So this whole thing will just become delta omega if this integrates to 1. For that, you need to check whether that will integrate to 1 or not. So check if the integral from minus infinite to plus infinite, a by a square plus omega square d omega is 1. Okay. It turns out that if you do this integrations, it will just become tan inverse of some expression. So use the integration knowledge that you have or check this out. You don't need this too much. You can take this. You will observe that this will exactly be equals to pi. So the area will be pi. Okay. So therefore here also we should have pi. So delta omega will integrate to 1. So if I just multiply it by pi, I will get the area to be pi. So therefore we will have this pi coming into the picture. So it will just multiply it with pi. So pi times delta omega will come from here. Okay. When omega is equals to 0. And this will get added to this particular expression. Minus j by omega. If you just multiply j in the numerator and denominator, this will just become 1 by j omega. Okay, so all these things are just manipulations. Okay, so I'm just doing some manipulations in the numerator, denominator, somehow I am getting a nice expression. So I'm getting to a nice expression. That's it. Okay, so what we have is the limit value is actually equals to pi times delta omega plus this minus j by omega. I'm going to write it as 1 by j omega. Both are same. So you just multiply j in the numerator and denominator, you will get back minus j by omega. Right? Because j square is minus 1. So this is, so far what we have found? We have found the Fourier transform of u of t. Right? So Fourier transform of u of t will be equals to pi times delta omega plus 1 by j omega, which looks really weird, but this is the correct. Okay. So I hope this is clear, and this is really, really important. So in week 10, the first and foremost thing you should understand and get comfortable with is this u of t's Fourier transform. Let me write it very neatly for you guys. So the Fourier transform of u of t is pi times delta omega plus 1 by j omega. And this is one of the most important thing that you have to learn in week 10. Okay. So once we have this, now we can find Fourier transform of a constant signal. Okay. So which is just a constant value. How? Again, I will write this C as C times u of t plus C times u of minus t. Right? I can do this, right? So I'm just rewriting C as C times u of t plus C times u of minus t. Now I know the Fourier transform. So this Fourier transform of C will simply be Fourier transform of the C u of t plus C times u of minus t. Now use the properties of Fourier transform. So this will just become C times Fourier transform of u of t plus C times Fourier transform of u of minus t. So what did I use? The property of linearity property, right? So I can write it like this. Now what happens? Just now we did this Fourier transform of u of t. So once we know the Fourier transform of u of t, this is just the reversal, right? So recall again the property. So if you have x of t's Fourier transform, you know what happens to the Fourier transform of its reversal, x of minus t. Anybody? Anyone? The question is, if x of t has Fourier transform as xj omega, what will happen to its reversal?
X of minus j omega.
X of minus j omega. Very good. So this will just, even the frequency gets negated. So x of j minus omega, which becomes x of minus j omega. Use the same thing here. So we just found out that Fourier transform of u of t is pi delta omega plus 1 by j omega. We will just substitute that. Let me take this out. And also shorten it a bit. Okay, so now C times this Fourier transform, we know pi times delta omega plus 1 by j omega plus C times u of minus this Fourier transform will be just in the frequency domain, you have to take, in place of omega, you have to take minus omega. So this will just become pi times delta minus omega plus 1 by j minus omega. Okay, if you try to simplify this, what will you get is this and this will get cancelled out, and delta omega is same as delta minus omega, right? So it's just an impulse signal. So you know delta omega is same as delta minus omega. Both are same. So if you both can be added together, then this will just become 2 pi c delta omega. So in the last session, if you guys are following me, I have actually written down the DC signal's Fourier transform directly, like a formula. So it will just become 2 pi, the same constant value times delta omega. And this is how we can prove that. Okay, so the Fourier transform of a constant signal will simply be 2 pi times c times delta omega. And this we can prove using the Fourier transform of unit step function. Right? So that is why this is really important to take away from week 10. Okay, so once you have this, you can also find the Fourier transform of sine t, right? SGN, SAGNT or SGNT, sine t. Okay, so what is sine t? This will be 1 if t greater than 0. This will be minus 1 when t less than 0. And at t is equals to 0, we usually will not, we don't define it. But in most of the books, they will just take it as 0. Okay, so when you see graphically, this is how it will be. Now, how can I write this sine t in terms of unit step functions? Again, so all these are practice for you guys. So you should really skilled in these particular things. So this is t and this is sine t. Now you have to write the sine t using the step functions, unit step functions. This is 1 and this is minus 1. Okay. So think about this. So sine t, I'm writing it now, but do understand how can this sine t be written like this. So this can be written as u of t minus u of minus t. Okay, so people who are interested, you can cross check. Okay, so once you have this, what else is left? You can straight away, if you want the Fourier transform of sine t, you just have to use, so if I want this, I just have to take Fourier transform of u of t and u of minus t. And we know using linearity, it can be written as Fourier transform of u of t minus Fourier transform of u of minus t. And we know Fourier transform of u of t, we know Fourier transform of u of minus t, and all is left. What else is left? We left with only computation. So if I finish this, this will just simply be u of t's Fourier transform is pi delta omega plus 1 by j omega, and u of minus t's is pi delta minus omega minus 1 by j omega, but there is minus outside. So if I take this, and again delta omega is same as delta minus omega, and this time these two will get cancelled out. 1 by j omega minus of minus 1 by j omega will just become 2 by j omega. This will just be 2 by j omega, and little bit careful here. Again, omega should not be equals to 0. Okay. So like this, for certain signals like this, you can actually find the Fourier transforms using the Fourier transform of unit step function. Okay. So that is one. That is why I said this Fourier transform for u of t is really important. That will help us solve Fourier transform of some other signals also. Okay. All right. So in the last session, we have discussed a few properties like what will happen when I shift the signal in time domain? What will happen to its Fourier transform? When the frequency shift happens, what will happen to its Fourier transform? When convolution in time domain, what will happen to its Fourier transform frequency domain? It will just get multiplied. When it is multiplied here, what will happen in the Fourier transform domain? It will just take convolution and scaled by 1 by 2 pi. So all these properties we have seen. Now we will see two more properties in week 10, which is differentiation in time domain and integration in time domain. Okay, so a couple of properties. First one is differentiation in time domain. So you have x of t, its Fourier transform is xj omega. Okay, so now I differentiate x of t. What will be the Fourier transform of this differentiator? Okay, so if you look this as another signal, then this is a differentiator. What will be the Fourier transform? Okay, so this is also quite easy. See, when you forget formulas or properties, always remember, use synthesis equation or analysis equation. So the connection between x of t and xj omega. So that if you know that, so all these things can be proven with that only. Okay, so as we know, x of t is 1 by 2 pi minus infinite to plus infinite xj omega e power j omega t d omega, right? So if I differentiate with respect to t on the left side, I should do the same thing on the right side too. If I do differentiation on the right side, you see 1 by 2 pi is independent of t, xj omega is independent of t. The only term that is dependent of t is e power j omega t. So you can directly take the differentiation of that particular term alone. Everything else is constant with respect to t. So if I do take the differentiation with respect to t, what I will get is 1 by 2 pi minus infinite to plus infinite x j omega, and e power j omega t when differentiated with respect to t, we will get j omega e power j omega t d omega. Okay, so what is there now? See, this x j omega is the Fourier transform of this signal, right? So as simple as that. So this will be j omega times x j omega. Okay, so now you should tell me what is the Fourier transform of d square x of t by dt square. So what do you think? So these things are important. So it may not be discussed in the lectures. This is how your thought process should be. Okay, so it's not about what you learn through lectures. It's about what you can derive or what you can think more apart from the lectures. So this has been discussed in the lectures. What happens to this? What is its Fourier transform? Just think. Or use the formula. Whatever we did now, use the same thing again. What do you think it will be? Anybody? Even though it is wrong, just guess, no? minus omega x j omega. Okay. Any other answers? See, you look at how we came from x of t to dx of t by dt. Yes, very good, Ashish. So this will just become, again, you just have to use this synthesis equation again. You take this expression now, you differentiate again with respect to t on both sides. Right? So you will get minus omega square or j omega whole square. If I have to be consistent with the previous expression, this will just be j omega whole square x j omega. Now you can generalize this, right? So you should not stop at 2. What if I take nth derivative? Right? So think about these things. So what is dn xt by dt power n? What is its Fourier transform? I will not give you, but by now you should be able to guess it at least. Right? So this is differentiation in time domain. When you differentiate in time domain, its Fourier transform will just become j omega x j omega. Right? So that is one thing. The second thing, we would like to, the second property is integration in time domain. Right? So we want to find the Fourier transform of integral minus infinite to t x tau d tau. Okay. So now again, so far we have been saying u of t is important, important, important. So now we have to write this in terms of u of t. Okay. So using x of t and u of t, can we write this, or think about this? Can we write this as xt convolved with u of t? So when I convolve u of t with xt, will I get this integral minus infinite to t x tau d tau? What is this? X t convolved with u of t. This will be minus infinite to plus infinite x tau u of t minus tau d tau. And what is this u of t minus tau? Where will this be positive? Or where will this be non-zero? This will be non-zero. This will be 1 when t minus tau is greater than 0. So the inside, u of whatever is inside should be greater than 0. Only then it is non-zero. And for other values, it will be 0. So when t minus tau less than 0, it is 0. So what are we getting? Our tau should be less than t. Only for those tau which is less than t, this expression u of t minus tau will be 1. For other values, it will be 0. So this integral will simply be, or it will be non-zero only in the interval minus infinite to t. Because after t, this u of t minus tau will become 0. So this will just be minus infinite to t x tau d tau, right? Which is same as the integration. So we are asking the Fourier transform of xt convolved with ut. So whenever there is convolution in the time domain, this will simply be in frequency domain. its Fourier transform will simply be xj omega into u of t's Fourier transform. And again, what is u of t's Fourier transform? This is pi delta omega plus 1 by j omega. Right? So this is the Fourier transform of this. Now if I simplify this, this is pi times x j omega delta omega plus x j omega by j omega. And again, look at this expression. Some function multiplied by delta omega. Do we know any properties to simplify this? So x of t into delta t. What will it become? X of 0 into delta omega will be there, no? Right, so recall all these properties. Xt into delta t will simply be, it will just sample the function value at t is equals to 0 into delta t. Okay, so this can be written as pi times x0 delta omega plus xj omega divided by j omega. Okay, so that is the Fourier transform of the integrator. Okay, so the differentiator and the integrator, these are also important, and you can get this even though you forget the formula, you can always get through from basics. Okay, so this is also important. All right, so far what we have discussed is, we have discussed the Fourier transform of u of t, right? Once we got the Fourier transform of u of t, we found the Fourier transform of the constant signal. We found the Fourier transform of sine t, and then we talked about two more properties, which is differentiation in time domain and integration in time domain. Okay, so let's solve some more problems. Okay, so let's say we'll take some we'll take this. So let's say x of t is sine 2 pi t into e power minus t into u of t. Okay, so now what we have to do is, we have to find the Fourier transform of x of t. Okay, so we have sine 2 pi t, e power minus t, and u of t also coming into the picture. So how do we find the Fourier transform? Okay, so I'll just give you 1 minute to think about this. At 8:45 we will start solving. Okay, so just think. You don't have to solve completely, but think how you can rewrite this expression so that computing Fourier transform will just become easier. Okay, and this is one of your practice assignment questions also. And do definitely solve practice assignment, graded assignment questions for your end-term preparations. Okay. Okay. So let's see how we can do this. The first and foremost thing is the sine 2 pi t. We know how to convert them to exponentials, complex exponentials, right? So once we do that, what is the advantage of doing that? We have e power minus t, which is a exponential, right? So if we rewrite this also an exponential, then we can club together and it will more or less look like e power something into u of t. And we know how to compute the Fourier transforms for them, for those. Right? So that's the idea. And once we get that idea, all we have to do is to execute it. So now sine 2 pi t can be written as e power j 2 pi t minus e power minus j 2 pi t divided by 2j. So once I write this, I'll just multiply it by e power minus t into e power minus t and then multiply u of t, u of t. Okay, so this will just become e power, this e power minus t, if I multiply, I'll get e power 2 pi j minus 1 of t minus e power minus of 2 pi j plus 1 of t. Right, so divided by 2j into u of t. Right, so this is our x of t. If I have to find the Fourier transform, I'll just simply use my formula. So this will just be minus infinite to plus infinite x of t e power minus j omega t dt. If I just substitute what x of t is, we will have e power 2 pi j minus 1 t minus e power minus 2 pi j plus 1 of t divided by 2j into u of t into e power minus j omega t dt. Right, so all these things we have. We can remove u of t by say, changing the limits. So u of t will be non-zero only in the interval 0 to infinite. So I can simply write this as 0 to infinite. U of t is 1. And we should multiply this e power minus j omega also. So if I multiply, the powers will get again added up. So we'll have e power 2 pi j minus 1 minus j omega of t minus e power minus of 2 pi j plus 1 plus j omega of t whole divided by 2j dt. Right? So 1 by 2j can go out. So if I write this 1 by 2j outside, and then all we left with is 0 to infinite e power, I'll write this little bit cleaner. So this will be 2 pi minus omega of j minus 1 t and minus integral 0 to infinite e power minus of 2 pi plus omega j plus 1. Right, so this into t, here dt and dt. Okay, so now it is just computation, that's it. So what is the integral of e power 2 pi minus omega j minus 1? So this all this thing is independent of t. This is also independent of t. So what will happen? The whole thing will come into the denominator, right? So this will just be e power, let's say this is some a and this is some b. So e power at's integral will be e power at by a and infinite and 0, right? You can do minus of because we have infinite here, no? So 2 minus of so we'll say minus of plus omega plus 1 minus 2 pi. Okay, so this will just become e power minus at divided by minus a. And this also will become e power minus bt by minus b. And here also limits infinite and 0. So this will 1 by 2j. So after solving, so when I substitute infinite, both of them will become 0. When I substitute zeros, both of them will simply become 1 by minus a. This becomes 1 minus minus and minus. So overall this will just become minus 1 by b. Okay, so here there is minus, here there is minus, and even if I substitute the limits, they will have another minus. So overall 3 negatives, it will just become negative. Okay, so what we have is minus 1 by 2j into a plus b divided by ab, where a is 2 pi plus j omega 2 pi j plus omega j plus 1, right? So minus 2 pi plus omega of j plus 1, and b is 2 pi plus omega j plus 1. If you substitute and if you try to simplify, you will finally end up getting, so there is a lot of calculations, substitution and calculation, you will finally end up getting very nice expression 2 pi by 1 plus j omega whole square plus 4 pi square. Okay, so treat that 1 plus j omega as one expression. So this 1 plus j omega is one expression and 2 pi j as another expression. So we will finally end up getting. So why is that? Because if you treat it like that, then A and B will just become complex conjugates to each other. Okay, so that is the advantage of taking it like that. So if you take that and when you multiply A and B together, it will just become that real part whole square plus complex part whole square, right? So that will just become 1 plus j omega whole square plus 4 pi square, 2 pi whole square, which is 4 pi square. Okay, so you just, so this is like an exercise for you guys. You just try to solve it and you'll end up getting this particular expression. Okay, so what we finally got is, we got the Fourier transform of this particular signal. So initially the signal can contain any kind of expression. So it is containing sine 2 pi t, which is sinusoid, e power minus t is exponential, u of t is unit step, and all three combined together is providing us like we can actually compute the Fourier transform without any difficulties. So the only difficulty comes here in calculation part. So if you take minus in place of plus and plus in place of minus, everything is gone. Okay, so be very careful about these computations, but the concept is important. So how should you solve a given particular problem? So problems like this, you should eliminate one kind of expression. So somehow you should eliminate that signs and bring everything into exponentials. Okay, so after that you can solve. Okay, so this is how you can actually find Fourier transforms for any finite signals. You just directly use the formula. Any infinite signals like this, u of t is delta of t. So delta of t is also important, which we did in the last lecture, I guess. So delta of t's Fourier transform is 1. Okay, so this is also important. So delta of t, u of t, and all the signals that we discussed so far. So these are really important. And this e power j omega t, right? Or e power j omega naught t. Its Fourier transform will be 2 pi delta of omega minus omega naught. Okay, so you can use the duality property and you can get this. This also I have done in previous live session. Just go back and watch it. Okay, so these are, so all signals and system more or less lies on 3 signals. Okay, so one is this Dirac delta, delta of t. Another one is u of t. And the final one is this exponential, complex exponential e power j omega naught t. If you understand these 3 signals, and if you understand all these transforms neatly, then you can derive any signals, you can analyze any signal. Okay, so that is the key takeaway that you should take from this signals and systems course. Okay, so signals and systems course is all about how these 3 signals, when put into some system, majorly LTI system, how are they behave? How are the outputs behave? What are the magnitude response, phase response, right? So what is the magnitude and phase of the outputs? So all these things you should really know about. All right. So this is one thing. The other major thing in week 10 is about the analysis of LTI systems using this Fourier transforms. So Fourier transforms and its uh, importance. Okay. So we'll move to the next concept that is dealt in week 10, which is Fourier transforms and LTI systems. Okay, so an LTI system can actually be analyzed using this Fourier transforms because the system can actually be described by its impulse response, right? So I'm not going back to LTI systems, how impulse response is sufficient to compute the output of any given input signal x of t, right? So an impulse goes in delta of t to an LTI system. We get the impulse response, which we denote it as h of t, right? So once we know the output to an impulse input to this LTI system, then I can find output for any x of t, any input x of t, right? So this LTI with frequency response h of t, what will be the output? A of t. It is going to be the convolution with input convolved with impulse response, right? Again, recall everything. See, whatever you study in previous weeks, everything will come back. So this we know. So once we know this and we understood that convolution is not that straightforward, what we will do is we'll take Fourier transform on both sides. Fourier transform on both sides. So if you take Fourier transform on both sides, you will have on the left hand side, you will have yj omega. On the right hand side, Fourier transform of convolution is product of its individual Fourier transforms, right? So this will just become xj omega hj omega, right? And this hj omega is called the transfer function which transfers xj omega to yj omega, or it is also called, in our course, it is called frequency response. So when we say frequency response, it is actually the Fourier transform of the impulse response. Okay, so this frequency response is Fourier transform of the impulse response of an LTI system. And this frequency response is yj omega by outputs Fourier transform divided by inputs Fourier transform. Right, so again, you just take this xj omega to the left hand side, you will have this. Okay, so what we got so far? So what we did is we got y of j omega, which is Fourier transform of the output. So if I have to get y of t, what I have to do? I have to do the inverse Fourier transform of. So the output y of t is inverse Fourier transform of yj omega. All right. So what we do is, instead of computing the convolution, instead of doing this, what we do is, instead of being in the time domain, we move to the frequency domain. We compute the product of its Fourier transforms, and that will be the output Fourier transform. And then looking at the output Fourier transform, we take the inverse Fourier transform. We compute the inverse Fourier transform, and that will be the output of this LTI system for the given input x of t. Okay, so that is one advantage of Fourier transforms, so in LTI systems. And this is majorly discussed in the first two lectures. You can go back to the lectures and look into these concepts. And then the next two lectures were on these problems that we discussed so far. Okay. And finally, through the end, so even again, the next 4 lectures, we have discussed the examples and everything. And the last lecture, again, the third most important concept that you should definitely solve problems, and you can expect problems from that particular concept, which is given the differential equation. Okay, so given the differential equation in terms of output and input, you should be able to compute the transfer function. So how can you compute the transfer function? This is one of the most important concepts, at least with respect to exam point of view. Okay, so you have a differential function, let's say an dn y of t by dt power n plus an minus 1 dn minus 1 y of t dt power n minus 1 plus and so on plus a1 dy of t divided by dt plus a naught y of t is equals to some x of t. Okay, so even the right hand side also can contain some differential equations. So it can also be dx of t by dt terms also can be there, but that is fine. We will not worry about that now. If you understand this, that can also be generalized. There is no difficulty in that. So what we are going to do is, we are going to find the transfer function hj omega. How can I find? I know that hj omega is yj omega divided by xj omega, right? So I have this differential equation that is satisfied by my output and input, right? And I have to find my output, right? So y of t. So if you solve this equation also, you'll get the y of t in terms of x of t only, right? So output input relation. So for that, to characterize that, it is sufficient to find the frequency response, which is hj omega. So to find that, what we do is, so this is in time domain. What we do is we take the Fourier transform on both sides. Okay, so take Fourier transform on both sides. So all these are some kind of applications of Fourier transform, advantages of Fourier transforms. So when I take Fourier transform on both sides, so I know dny. So if y of t has, just now we discussed, if y of t has capital Y j omega as the Fourier transform, then if I do the nth derivative, its Fourier transform will be j omega whole power n capital Y j omega. Okay, so I gave it as an exercise, but that is what it will be. So dn yt dt power n, Fourier transform will be j omega whole power n y of j omega for any n. Okay, so if it is n, this is how it will be. If it is n minus 1, j omega whole power n minus 1. If it is n minus 2, j omega whole power n minus 2, and so on and so forth. Okay, so if I take Fourier transform, if I take the Fourier transform, first term will just become an j omega whole power n y of j omega plus the second term Fourier transform will be an minus 1. And again, the sum, if I take the Fourier transform of the sum, it will just become sum of Fourier transforms. Correct? Using linearity again. So this will just become j omega whole power n minus 1 y of j omega. So like this plus a1, this term. This will be a1 j omega y of j omega. And the last term will, on the left hand side, will just be a naught. Y of t's Fourier transform is y of j omega. And the right side, if I take the Fourier transform of xt, it will just become capital X j omega. So left hand side, if you again see, every term has y of j omega. So you can pull that out. So if I pull that out, first term will be an j omega whole power n, an minus 1 j omega whole power n minus 1, plus and so on, plus a1 j omega whole power 1 plus a naught is equals to x j omega. So now what I will do, I will take this whole thing to the right side and this x j omega to the left side. So if I do that, I'll get y j omega to be y j omega divided by x j omega to be 1 by an j omega whole power n plus an minus 1 j omega whole power n minus 1 and so on. Last term will be a naught. And this y j omega divided by x j omega is nothing but our transfer function, which is h j omega. So once we get h j omega, if you know how to take the inverse Fourier transform, we can get the impulse response. So once we know the impulse response, we can get the output input relation directly, right? So any given input, we can actually find its output. So you don't have to solve this differential equations anymore. Okay, so these differential equations can be solved using the idea of Fourier transforms. Okay, so let's do one problem on this differential equations, which is, I think, let me take from practice only. Okay, so just a second. Yeah. So let's take this particular question. Let's take d square y of t divided by dt square plus 5 dy of t by dt plus 6y of t is equals to 4 dxt by dt. So see, dxt by dt is also, we know how to take the Fourier transform of it, right? So now if the question is find hj omega, what we will do, we will take Fourier transform throughout. We will take the Fourier transform throughout. We will get the Fourier transform of d square yt by dt square will just be j omega whole square capital Y j omega plus 5 j omega into capital Y j omega plus 6 into capital Y j omega is equals to 4 times the Fourier transform of dxt by dt will be j omega into x j omega. Okay, so now separate out y j omega x j omega divided by x j omega, which is your h j omega. So if I separate it out, our h j omega, which is y j omega divided by x j omega, which is 4 j omega on the right side divided by j omega whole square plus 5 j omega plus 6. Right, so if you simplify this further, the numerator will be 4 j omega divided by j omega whole square will just be minus omega square, right? So, or you can factorize this, right? Or just leave it like that, that is fine. So 5 j omega plus 6 minus omega square. So if we were asked you to compute just the frequency response, which is capital H j omega, you can just give this particular expression. If we had asked you to compute the impulse response, which is h of t, right? So we ask you to compute, find h of t. What will you do? H of t is the inverse Fourier transform of capital H j omega. But as far as we know, we don't know how to compute the inverse Fourier transforms, right? But at least for few Fourier transform pairs, you should know, right? So such as if you have e power minus at u of t, you know that its Fourier transform will be 1 by a plus j omega, right? So this we know. So that means if I have to find the inverse Fourier transform of 1 by a plus j omega, this will be e power minus at u of t, right? So Fourier transform, inverse Fourier transform, right? It's like inverse. It's function out input output, and if you have output, if you do the inverse, you should get the input back. So that is what it is. So this particular pair is really important, right? So most of the questions may just use this particular thing. Okay, so even here also, you will see that you can actually do partial fractions and separate it out. And then you can actually use this Fourier transform pair and find the inverse Fourier transforms. And you'll get the expressions in terms of e power minus at and u of t. Okay, so maybe I will leave this to you guys to think about it. If not, we will anyway do these problems in Saturday session. Okay, so what we discussed in this particular session is three major things, which when you go back after this session, spend some time tomorrow and day after tomorrow on these concepts. The first and foremost thing is you should know how to find the Fourier transform of the unit step signal, which is u of t. Okay, so that is really important. That will help us to compute other Fourier transforms also. And these two properties. The next thing is when you do differentiation in time domain, what will happen to its Fourier transform? And when you do integration, what will happen to its Fourier transform? So integration looks quite squarey, but if you know u of t's Fourier transform, then this is very easy, right? So that is the second thing, which is really important in week 10. And the third thing is how can we simplify the analysis of the LTI systems, right? So earlier we have to compute for output, we have to compute the convolution. Convolution is very difficult in some sense. It involves integration and all. So integrations is like time taking thing. But if we introduce this Fourier transforms, how can we simplify the analysis, right? So it will just be the product. And then once we have h j omega, which is a frequency response, we will take the inverse for, once we have this capital Y j omega, the output's Fourier transform, we will take the inverse Fourier transform of it, and that will be the output. Okay, so for inverse Fourier transforms alone, I said you just read this out. We will do this inverse Fourier transforms in detail on Saturday session. Okay, so and the last thing that is really important is given a differential equations like this, how can I get the input output relation, right? So for that, I need to get the impulse response, which is h of t. So once I know the impulse response of this LTI, then I can definitely find for any input, I can actually find the output, right? And Fourier transforms will help us to get the frequency response first, then use the inverse Fourier transform and then get the impulse response. And once we have the impulse response, we will completely describe the LTI system, right? So these four are important concepts in week 10. Now, those who have watched the lectures will know all these things. If you haven't watched the lectures, now I suggest you go back to and watch the lectures. It will be much more clearer for you guys. Okay, so solve more problems on this. And on Saturday, we will solve some 3 to 4 problems, which will help us to solve graded assignment problems, as well as we will understand this idea of inverse Fourier transform. Okay, so how to compute inverse Fourier transforms of some expression, something like 1 by aj omega. So you know the inverse Fourier transform is e power minus at. What is the inverse Fourier transform of 1? Right? So these are all some standard pairs that you should know. Inverse Fourier transform of 1 is delta of t. Alright, so these things you should know. Okay, and inverse Fourier transform of e power minus j omega some t naught. Okay, so this will be delta of t minus t naught. It is just the shifting. Okay, so all these things we'll see on Saturday. Any doubts on what we discussed so far from anyone? Okay, so before you come to the Saturday session, what I want you guys to do is solve all practice assignment problems and then come on Saturday, okay? So that whatever we do on Saturday will be much more clearer for you guys. All right, so let's meet on Saturday then. And if you have any doubts, you can ask, or else we can end the session. Okay, so silence, I will take it as no doubts. Okay, so thanks all then. We'll meet on Saturday. Yeah, no more problems. We'll do more problems on Saturday. Okay. So we have done a couple of problems, like 4 or 5 problems, I think. Right. So we have computed Fourier transform for 3 signals, and then this example and this example. Okay. So we will do week 10 and 11 have the same deadline. Okay. We'll look into it. If possible, we will just try to push the deadline for week 11. Yeah, but there will be live session for week 11 also. Okay. All right, guys, then. Let's meet on Saturday. Good night.